Given a drawbridge that has a mass of 45 kilograms and that the donkey on it has a mass of 65 kilograms, if the drawbridge has a length of 4.5 meters, the rope holding it up is wound up in the castle at a height on the wall of 5.5 meters. So I imagine there's some like little hole the rope goes in there, and then there's some kind of thing, maybe spool or something that it's wound up on. Anyways, and the donkey is standing at a point 3 meters from the castle. What minimum tension should the rope provide? So this is a pretty complicated situation, probably the most complicated we're going to look at. And definitely if we just try to write a seesaw equation and guess the answer, it's probably going to be too hard. But if we draw a good picture of the forces and kind of structure our reasoning, it should be possible to do this. So I'd like to start by, again, drawing those forces, kind of an extended free body diagram point of view. So I'm just drawing a line here that kind of represents the drawbridge, and I'm going to look at all the forces applied to it. Now, I think there's going to be a force corresponding to the weight of the bridge itself that's going to be at about halfway its length. So maybe that's that force right there. Maybe I can just say that's the force F sub B for the bridge. Then the donkey is, because like this full length is 4.5 meters, so I guess this would be like at 2.25 meters, but donkey is at 3 meters. He has slightly larger mass than the bridge itself. And so I'm going to draw this force here and call that F sub D for the force of the donkey. And then in the picture, there is this rope that is applying the tension force that holds all of this up, I guess, all the way at the right end there, but it's at an angle. And that's part of what makes this question maybe a little bit difficult, is we're going to have to kind of study that angle a little bit. I may not get all the lengths on these forces perfect here, but I'll just label that as a tension force. Now, it turns out there are also forces here at the left end of the drawbridge where it kind of connects to the castle. Maybe there's some kind of hinge system or whatever there. But however that works, there's definitely got to be some forces there, because probably there'd be a force there that supports part of the overall weight that is on this system. In other words, I think there's a component of this tension force that's kind of counterbalancing these two weights that are on the system. But I don't know if that's going to be enough by itself. So there's probably some force there at the drawbridge that's going to help with that. But since the tension force is also at this angle, there'd need to be some horizontal force applied there as well that would kind of counter the horizontal component of this tension force here. But these two forces, I got no clue about what they are. And if I chose maybe an inconvenient way of doing this, maybe I'd have to find what they are. I've just put question marks. But I'd like to take the approach to this problem that we simply look at the balance of the torques adding up to 0. So if I choose the point, and I like to say that it's the origin, but you could also say it's where the rotation axis for the system is, and that kind of makes sense, right? The drawbridge would rotate around that point. But it turns out for static problems, you're actually kind of at liberty to choose where you place it. So I like to call it origin, because you could actually place it somewhere that maybe it wouldn't make any sense for the system to rotate around. But it just so happens that it does here. But again, origin, it's also maybe shorter, right, I guess, than rotation axis. I guess you could just say axis, right? But anyway, so if you want to do that, go ahead, right? Not everyone has to do things exactly the same way, which is really, really nice. So how am I going to approach this? Well, one issue I think that's going to come up is there's definitely some angle that is not trivial for this tension force. And I'm going to define an angle theta right here to help me think about that. And based on the picture, I know that that tension force points in the direction of this rope that is holding up the drawbridge. And there's kind of a triangle here, right? And if I go back and look at the numbers that I'm given, right, the drawbridge has a length of 4.5, and the rope is kind of going into the wall at a height of 5.5. So based on that, I think I can draw the following right triangle that should contain as one of its angles the angle theta here. And based on those numbers, the two legs should be 4.5 and 5.5. And I think I'm going to wind up using this later on to find, like, do some trigonometry with that angle theta. So I'm just going to leave that there as useful information. Let's go ahead and look at the torques again with this origin. The convenience of placing it there means I don't need to know these forces. They have 0 moment arm. They're not going to count. So really the only torques I need to think about are the torque of the, let me actually start. I'm changing my mind. I was going to start with the bridge, but I'm going to start with the tension force. I'm going to say the torque due to the tension force. The reason why I'm starting with that one is because that one I think kind of rotates the drawbridge upward, right? Which really is like a counterclockwise direction, whereas the two weights, the one of the bridge itself and the donkey, are pulling it in the opposite direction, making the bridge go down or rotate in a clockwise direction. So I'm going to be explicit about my minus signs with that already at this step, and so therefore say, okay, there's a torque due to tension, but that's going to counterbalance the torque due to the weight of the bridge itself and the torque due to donkey's weight applied to this system. And I'm saying that those things must add up to 0, but explicitly recognizing really it's this torque subtract the other two that's going to wind up doing that. Now, recall that the definition of torque is equal to RF sine theta. So I'd like to use that to kind of start to figure out what these different things are. Now, this is a pretty complicated situation, and I could invent a whole bunch more variables, like maybe an R sub B or an R sub D, maybe even an R sub T, or maybe just R1, R2, R3, or whatever for moment arms for these different torques, these three that I have. But maybe in this case, I'm going to relax what I usually do in terms of working with variables and putting in numbers only at the very end. Maybe it's cool if we put in some numbers already. So if I think about the torque due to this tension force, the moment arm length for that, I think, is equal to 4.5 meters, right? So I'm just going to put in 4.5 meters there. However, I don't know what the tension force is, so this is going to look a little bit mixed because I'm going to have kind of numbers mixed with symbols, and that'll make it kind of obvious what to solve for. So it's okay to do this sometimes. It's not something I often like to do, but it does sometimes save a little time from inventing a lot of variables. It does mean that my expressions are going to get longer, though, so that's kind of maybe the drawback. I'm just going to put sine theta for this one and delay working on that because I know that this is going to be the theta that's in this triangle, because this torque due to the tension force, that's the one that's got this weird wonky angle in it. The other ones are kind of at right angle to their moment arms, and we've already explicitly dealt with the direction of rotation. So for those, I think I can just say, let's see, for the bridge it would be minus, I think its distance there would be half of 4.5, so I'm going to put in 2.25 meters. And for the weight of the bridge, I'm just going to say that it's 45 kilograms multiplied by G to save a little space. Like, this is maybe something worth appreciating. If I put in 9.81 meters per second squared and just keep going like this, this expression may become explosive. So I'm just going to use G for short there. So again, I'm kind of mixing my usual methods a little bit here by throwing in numbers, but I thought it might be easier to look at for this. Maybe I'll be wrong. So if you wanted to invent variables for this and do it that way and then plug in numbers at the end, that's okay, right? But I'm choosing to do it this way right now. Anyway, so I'm starting to do donkey now. I've put in 3 meters because it says that donkey is standing at a point 3 meters from the castle. I'm going to kind of assume that that means that donkey's center of mass point is 3 meters from the castle, even though one might say if you told this to maybe any old person that's not in a physics class, they might not interpret it that way, right? But I'm going to interpret it that way because we weren't really told what donkey's width is, right, or length himself, and so this is the only assumption I feel like I can make reasonably. His mass is 65 kilograms, and so really what I'm doing here is I'm saying torque is equal to moment arm times force, but since these two are both at right angles to moment arm, I know sine theta would just be equal to 1, or I don't know, maybe it's minus 1 because of this minus sign here. But that's just because I'm accounting for the direction of rotation in a conceptual kind of way. But if this really is representing weight, that's why I'm multiplying by G for both of these. I just want to make sure we're all kind of on the same page with that. And all of this is still equal to 0. I barely had enough space to fit all that in. Okay, but it does maybe make it kind of obvious how I could possibly solve for this force here. I'm just going to isolate it, right? The other thing I might recognize is now that I've done, or kind of, done this, right? What trigonometry do I actually need from this triangle? I need to be able to figure out what a sine of theta is. And so sine is normally opposite over hypotenuse. Maybe what I could do, instead of doing something extraordinarily complicated, is I'm just going to solve for the hypotenuse of this triangle by taking 5.5 squared plus 4.5 squared and then taking the square root. And what I get for that on my calculator is 7.106335202, but maybe I think we're going to be working at like a 2 sig fig level by the end here, which is not that many. So maybe if I just keep a couple extra is good enough. So I'll put in that hypotenuse of 7.106 there, and then recognize that the sine of that angle can be expressed as the ratio of 5.5 over 7.106. And that will be a very practical thing I can just put in for this when I solve here. So at this point, though, not having a ton of space here and these expressions being rather long, I'm going to say maybe if you want to, you can pause this and see if you can do the algebra yourself to get for the expression of this force. But I'm just going to go ahead and start writing it. So again, pause if you don't want to see it yet and you want to try it and then compare to mine. But here it is, I think. So let's see. Maybe I shouldn't have made that much space there. All right, that part's coming from there. And then I'm going to add this part as well. So I factored out a common factor of g, so I'm going to multiply up here. I'm going to put that in explicitly as 9.81 meters per second squared. I barely have enough space for that. Maybe I shouldn't have used up this gigantic space right here. That was silly, I guess, right? And then I'm going to divide by 4.5 meters times sine of theta, but we're recognizing that the sine of theta is equal to 5.5 divided by 7.106. All right, so that's what I got. Hopefully you got the same thing if you pause it and try doing the algebra yourself. And now my next step, that is also maybe not so trivial really, is to take all of this and calculate it, right? And so enter that correctly in the calculator. And I would also encourage you, if you want to, pause the video and do that, and then compare that to the answer that I get, because these are important skills. Sometimes we do these large calculations, and it's a good idea to kind of be practicing that as we go. So I get for that like 834.4059. I haven't rounded or anything here. Newtons with those numbers put in. I did already round with this number a little bit though. So this, in that sense, really, these digits out here shouldn't be regarded as being certain at all. But again, this is literally what my calculator said. But now, as my last and final step, I'm going to round to an appropriate place given the maybe certainty of the numbers that I've been given here. And I'll round it off to two significant figures and say 830. I would say, though, if somebody said 834, I'd be all right with that. I'm not like super picky again about sig figs. I don't believe in marking off lots of points for that, but it's kind of a guide for final results. It's just worth recognizing any result. If these were based on real measurements, there's always going to be some amount of uncertainty. And so some amount of rounding is always going to be tolerated. In that sense, reporting this as a final answer is like grossly exact compared to what we would expect to happen in reality, right? But anyways, let's check that 830 newtons and see if it worked out. Looks like it did.